The Great Dimming Event, which occurred in late 2019 and early 2020, saw Betelgeuse lose over 60% of its brightness. This striking phenomenon captivated astronomers around the world and fueled speculation about the star's potential explosion. Betelgeuse's surface is marked by massive convective cells that create its irregular brightness and distinctive look. These cells shift like slow-motion storms, directly influencing the star's luminosity. Unlike the Sun, Betelgeuse has a significantly shorter lifespan of about 10 million years. This leads to a rapid consumption of stellar fuel, ultimately resulting in a supernova explosion. The slow rotation of Betelgeuse may stem from its angular momentum being spread over a vast volume as it expanded into a supergiant. This mirrors the way an ice skater slows down when they spread their arms. In contrast, fast-rotating massive stars encounter extreme atmospheric conditions, resulting in oblate shapes and the possibility of material escaping into space. This is different from the more uniform mass loss seen in slower rotators like Betelgeuse. The distinct rotational histories of Betelgeuse and Antares suggest they follow different evolutionary paths shaped by mass loss and interactions with potential companions. This highlights how mass loss can influence rotational speeds over time. The unpredictable behavior of VY Canis Majoris, with its dramatic brightness fluctuations, poses challenges for astronomers trying to predict its future. Its significant mass loss could lead to a direct collapse into a black hole. When comparing VY Canis Majoris to stars like Betelgeuse, scientists observe varying stability levels and mass loss rates. This contrast aids in understanding the different stages of star evolution. Studying VY Canis Majoris enriches our knowledge of galaxy evolution, as the heavy elements it creates are essential for the formation of new stars and planets. Its extreme instability provides valuable insights into the behavior of massive stars. Monitoring the long-term brightness of supergiants reveals patterns signaling the end of a star's expansion phase. This tracking is crucial for comprehending stellar evolution. Simulating the physics of stellar interiors allows scientists to explore various scenarios of supergiant evolution, accounting for factors like mass and rotation speed. This helps enhance their understanding of stellar development. The low density of supergiants, despite their immense size, highlights a paradox in the balance between gravity and nuclear fusion forces. This unique structure significantly impacts their stability and ultimate fate. Astronomers have proposed two main explanations for Betelgeuse's dimming: internal surface changes or a dust cloud blocking its light. Both theories have been examined through extensive telescopic observations. The dimming observed in 2019 allowed astronomers to study Betelgeuse's transformation in real time. This was linked to a massive outflow of hot gas and subsequent dust formation, shedding light on the star's dynamic processes. Despite the unusual dimming, Betelgeuse returned to its normal brightness by mid-2020. However, questions linger about its future, making ongoing monitoring of similar stars essential for understanding these transient phenomena. The chaotic mass loss experienced by a red supergiant can disrupt nearby planetary orbits and atmospheres, potentially ejecting surviving planets into interstellar space. From the material expelled by the star throughout its lifetime, new planetary bodies could form. These second-generation planets would differ significantly from traditional planets found around stable stars. The eventual supernova explosion of Betelgeuse releases tremendous energy, potentially obliterating nearby planets. Yet, some distant planets might endure, experiencing effects from radiation and shock waves. Stars with low metallicity enjoy a longer main sequence phase, allowing for more efficient fuel burning and delaying their transition into supergiants. This efficiency derives from their hotter and more stable cores. Metallicity variations across the Milky Way influence the behavior of massive stars depending on their location. Generally, stars at the galactic center are more metal-rich compared to those found in the outer regions. With slightly lower metallicity than the Sun, Betelgeuse exhibits unpredictable atmospheric behavior, characterized by rapid dust production and irregular heating patterns. This challenges conventional models of red supergiants. Neutron stars form when a massive star's core collapses, failing to reach the mass needed to create a black hole, resulting in a dense object about 20 kilometers wide. The core mass during collapse determines whether Betelgeuse will become a neutron star or a black hole. The Chandrasekhar limit, approximately 1.4 times the mass of the Sun, plays a critical role in determining Betelgeuse's fate. Should its iron core surpass this limit, it may collapse into a black hole instead of a neutron star. Astronomers are actively monitoring Betelgeuse for any signs of its impending explosion, such as increased brightness and neutrino emissions. These indicators could provide crucial warnings that the supernova event is approaching. While Betelgeuse displays unpredictable brightness changes and a moderate mass loss rate, VY Canis Majoris is characterized by extreme instability and rapid material loss. These traits underscore their differing end-of-life processes. The immense size of VY Canis Majoris, estimated to be 1,400 to 2,000 times the Sun's radius, sharply contrasts with Betelgeuse, which is about 1,000 times the Sun's radius. This highlights the incredible diversity found among massive stars. Both stars are luminous, but VY Canis Majoris significantly outshines Betelgeuse, rapidly consuming its nuclear fuel and leading to a shorter lifespan. This swift fuel consumption is typical of the most massive stars. Star formation involves gravitational interactions, turbulence, and shock waves that compress gas, paving the way for massive stars' birth. Stellar nurseries create the necessary conditions for this process. Supergiants evolve from small gas cores that collapse under gravity and ignite nuclear fusion. Over time, they grow tremendously, but they face limits imposed by radiation pressure. Supergiants often become runaway stars, drifting away from their original clusters due to gravitational interactions. This separation impacts their evolution and stellar dynamics within galaxies. Supergiants like VY Canis Majoris experience extreme mass loss, raising questions about their lifespans. This could influence the timing of their explosions as supernovae or their collapse into black holes. The interiors of red supergiants may harbor exotic forms of matter, including strange matter. This presence could fundamentally change how these stars evolve and eventually explode. Searching for exotic matter, such as axions and magnetic monopoles, might clarify unusual stellar behaviors. Understanding these may explain variations in supernova explosions and energy generation. Dyson spheres might stabilize stars or manipulate stellar evolution, potentially preventing supernovae while harnessing energy for advanced civilizations. This technology may extend beyond current human comprehension. A Dyson sphere could serve as a mega-observatory, allowing civilizations to study extreme astrophysical conditions and chaotic processes in red supergiants like Betelgeuse. Although supernovae are destructive, they can create conditions that foster life by distributing vital elements and triggering chemical processes essential for life's emergence on nearby planets. The turbulent convective currents within red supergiants can span millions of kilometers, forming fractal-like structures in their energy transport. This results in a chaotic and unstable surface appearance. This chaotic nature of energy transport in red supergiants contributes to their unpredictable mass loss. Such variability can profoundly impact their life cycle and eventual supernova events. Quantum effects may also influence the behavior of red supergiants, enabling energy movement through dense interiors in ways that classical physics fails to explain. This could lead to unexpected brightness fluctuations. An exotic fusion process could allow Betelgeuse to sustain reactions at lower temperatures than normal, indicating a unique behavior in its core. This challenges existing fusion models. Neutrinos generated during Betelgeuse's fusion might offer early warnings of its impending supernova. Monitoring these emissions could unveil critical insights into its final stages. Advanced neutrino detectors are crucial for observing Betelgeuse's behavior. These tools will assist scientists in monitoring its core reactions and predicting the timing of its supernova explosion. Supernovae frequently occur in clusters, particularly in areas like Orion, where massive stars abound. Their deaths can influence one another, shaping the future of their stellar neighborhoods. The shock wave resulting from Betelgeuse's explosion may compress gas and dust, potentially accelerating the formation of new stars within the Orion molecular cloud complex. Nearby systems might experience disruptions following the explosion, with the intense wave of particles possibly stripping atmospheres or altering planetary gravitational balances.